The Supersonics project is about bringing about the next revolution in air transportation. The next logical step is to make sure that we are able to travel at speeds that are faster than those that we have traveled at for the last 30 years.
The Supersonics project has set its sights high. Efficient, comfortable, long-distance flight at twice the speed of the current subsonic commercial fleet. If we can gain a better understanding of travel in the supersonic regime and overcome the key challenges presented by such flight.
The Supersonics project is putting together technologies that will ensure that we can fly these affordably, and furthermore, that these vehicles can fly around with much lower environmental impact than anything that we have seen today.
Every year, more people travel by air, across the United States and to destinations overseas. Supersonic travel could help to move more people faster. NASA envisions a new generation of supersonic aircraft that would be efficient, lightweight, and durable, with reduced emissions and takeoff and landing noise, as well as a reduced level of sonic boom, the jarring sound caused by the pressure wave from an aircraft flying at supersonic speeds. Much has been learned about the nature of sonic booms, but more knowledge is needed regarding how to design aircraft for reduced boom.
The ARMD effort has a multi-year project to assess various parts of sonic boom, both propagation, the shape of the vehicle, and the response of houses shaking from sonic booms.
Indoors, the boom takes a different character. The structure responds to the overpressure of the sonic boom. And so the annoyance or the way you perceive, the way people would perceive a boom is different.
It's the slope of the curve at which the sound pressure reaches the ground. So if we can have the slope on that more gradual, then the startle factor goes way down.
We use an F-18
and fly it at supersonic speeds, but in a way such that the sonic boom that it produced was actually similar to what we think we can achieve with our low sonic boom designs. We had about 4 different companies represented. We also had the FAA.
At the ground we had a lot of microphones
to measure the acceleration of the walls, the internal acoustics. We'll then take that data and incorporate it into improved models.
As part of the effort to reduce the strength of sonic booms, the Supersonics project worked in partnership with Gulfstream on an innovation in supersonic flight, quiet spike.
By having a telescopic nose, the usual very loud sonic boom off the front of the airplane is broken up into a series of small sonic booms. So instead of a loud bang on the ground, you get a series of pops. Underneath the aircraft, we flew another F-15 instrumented with pressure and position sensors, and we actually probed the shock field and measured what the shocks were doing off the quiet spike.
Sonic boom is the obvious starting point for research into overland supersonic travel and part of a broad focus on the overall performance and efficiency of supersonic vehicles. The development of improved computational tools will help to predict and improve the aerodynamics characteristics of future supersonic aircraft in such key areas as drag and sonic boom.
On the airframe, you have issues associated with turbulent boundary layers, excessive drag, airframe surfaces.
A large part of the success of this aircraft will come from how the aerodynamics, the structure, the propulsion, all are integrated in a system fashion.
We've had 30 years of experience with the Concorde in flight. We know its engine characteristics very well.
The engines, if they were sitting out in the airstream, like a regular commercial airplane, would cause a large component of the boom.
For us to beat the noise problem, we have to integrate the propulsion system within the airframe. This helps us both with takeoff noise and with the sonic boom problem. Taking a boundary layer from the airframe itself, ingesting that into the engine. This is turbulent, dirty flow, and the engine would like to have nice, clean flow.
The supersonic inlet operates using shock waves to decelerate the flow. When the shock waves interact with the boundary layers, it can cause separation. And so if we put these flow control devices just upstream of the shock interactions, we can attempt to reduce that separation.
Our academic partners, both Stanford and Illinois, are working on improving the computational tools so that we can improve our accuracy in our predictions. It's much cheaper than going into a large wind tunnel to test them.
Project research into engine technologies includes work to reduce harmful emissions into the atmosphere that could inhibit future supersonic flight.
For subsonic aircraft, emissions will actually increase the ozone. Supersonic aircraft fly higher, and at those altitudes, NOx emissions decrease the ozone. We're doing CFD modeling specifically for conditions that you might find in a combustor operating at supersonic cruise. Particulates are especially important.
Particulates continue to evolve as they leave the engine. You have secondary aerosols form. SC-11 uses a combustor to simulate the combustor of a jet engine and then exhaust into the altitude chamber. That allows us to study what happens to the particulates as they go up into an atmosphere in conditions similar to what you would have in supersonic flight.
A related issue involves the significant levels of noise produced by supersonic jet engines during takeoff and landing.
The biggest problem that we have in supersonic aircraft in noise is that they will need to have a much higher thrust level, but when they're near an airport, they have to sound much the same as a conventional airplane.
When we take off, and we must be in a quiet mode, we need large bypass flows. However, when you get to altitude, the bypass flow would not produce sufficient thrust, so you must pass all that flow through the main core of the engine.
To design an airplane, you have to be able to predict the sound that is made from it and be able to say when somebody says, how about a variation that'll make it more efficient or make it faster, you have to be able to tell them how much louder it will be. What we're doing here is creating a database of noise and flow conditions that are useful to understand how you predict the noise.
Commercial supersonic aircraft will need to be extremely durable at high speeds, high temperatures, and high altitude.
We've got a large number of efforts underway looking at some of the key fundamentals of materials for both the propulsion system and the airframe, particularly how to increase the life of those materials.
Military aircraft only fly supersonically for a short period of time. For commercial supersonic cruise, the engines will cook at 3,000 degrees for 3-4 hours, and they will glow red hot.
If we were to have to build a supersonic engine today, it's most likely the fan case would be a metal structure. So we want to have a good understanding of how a baseline material might perform so that we can gauge the benefits of putting a carbon fiber reinforced polymer in its place. So you take traditional resins and you add nanoparticles to those, which can improve the overall stability of the material. We have a group developing advanced structural ceramic materials that are really targeted at the hottest parts of the engine, the turbine.
If this plane may be in service 50 or 60,000 hours, the strength of materials tend to wear down over long periods like that at high temperatures. And the other differentiator is the altitude you're flying at, typically 50 to 60,000 feet. Under internal pressure load in the fuselage, we'll get to a point where it'll start unstably propagating. That's called fast fracture. We are looking at methods to analyze the residual strength of the structure after a breach of integrity. This is an idealized stiffener, not nearly as complex as on a real aircraft structure, but it'll give us a first look at how an extending crack might interact when it hits this stiffener. Will it go under it? Will it turn? Will it be arrested? These are the kind of things we'd like to be able to understand.
When I talk about aeropropulsive servoelasticity, the first part is aeroelasticity. That involves aerodynamics in the structure and how the structure and the aerodynamics interact, so you can have something bouncing around being driven by the aerodynamics. If you go beyond a certain condition, it can be very dangerous where the wing or the aircraft goes unstable and it can lead to destruction, the condition known as flutter. The servo part comes in, which is the controls. Can we now add control systems to try and compensate for any adverse aeroelastic effects? And the P for propulsion is, let's realize that as this wing or this vehicle is bouncing around and flexing, that might be affecting the engine performance because the engines are moving along as well. What we're seeking to do is understand the aeropropulsive servoelastic properties of supersonic transports and doing it in two ways. One is computational methods, look at different computer models to try and predict those dynamics, and then wind tunnel tests.